Greetings everyone. In preparation for the Calculus 1 course, we are still examining introductory topics. In this section, we will learn how to factor higher order polynomials. By higher, I am referring to third order or more. When it gets to third or higher order polynomials, factoring may become a bit more of a headache than it was the case for quadratics. In this section, we will present methods to factor such polynomials. Factoring by grouping should be at the very least attempted, but there is no guarantee this approach will be successful. For instance, were you to try factoring the third order polynomial x cubed minus 3x squared minus 4x plus 12 by grouping, the first pair of terms highlights a common x squared. The second pair of terms seem to have a common factor 4. And therefore x squared can be extracted from the first pair of terms, minus 4 from the second, to generate common x minus 3's. Because x minus 3 is a simple factor, it can be extracted, leaving x squared minus 4 behind. And for those who recall their special factoring forms, you'll recognize x squared minus 4 is actually a difference of squares. So in this example, x cubed minus 3x squared minus 4x plus 12 can be decomposed into three first-order factors: x minus 3, x minus 2, and x plus 2. In this second example, we're going to try to factor using, once again, grouping the third order polynomial 2x cubed minus 13x squared minus 10x plus 21. No simple factoring is possible, as 2x cubed, 13x squared, 10x, and 21 have no common elements. If we proceed by grouping, we can recognize x squared is common to the first pair of terms, and that 1 or minus 1 is the only common element to the last pair of terms. That said, the terms that are left behind, 2x minus 13 and 10x minus 21, are not identical, and therefore we cannot proceed by simple factoring at this stage. So we have to rethink our approach for an example such as the one we're confronted with right now. To approach such problems, we're going to discuss the factor theorem and use it as a tool to factor higher order polynomials. Here's what the factor theorem says. If p of x is a polynomial, and if p calculated at x1 is 0, in other words, if x equals x1 is a 0 of the polynomial p of x, then x minus x1 will be a factor of p of x. Sounds very sophisticated. We'll see how we can apply it in a second. In this example, we're going to start by showing that x equals 1 is in fact a 0 of 2x cubed minus 13x squared minus 10x plus 21. And then we'll try to figure out what that means about the polynomial. Well, first of all, let's name 2x cubed minus 13x squared minus 10x plus 21 as p of x. We're going to give it a functional notation here. Calculating p at 1 means replacing all x's by 1. And the outcome of this calculation is that we're going to get 0. This means that x minus 1 will be a factor of the polynomial, since x equals 1 was a 0 of the polynomial itself. That's what the factor theorem says. So what it entails is that 2x cubed minus 13x squared minus 10x plus 21 can be written as x minus 1, one of the factors it contains, times something. I've called q of x the expression that x minus 1 has to multiply in order to reproduce what we had originally, which is the 2x cubed minus 13x squared minus 10x plus 21 term. So q of x will be a polynomial of its own, in this case of degree 2 for the powers to match, that we're going to have to identify. Q of x can be found by simplifying the quotient, 2x cubed minus 13x squared minus 10x plus 21 over x minus 1, in other words, by performing long division, or by using a process called synthetic division, which is a bit of an accelerated way of doing long division. I'm going to show you quickly how we can perform synthetic division. Okay, so the idea is we construct a table where the coefficients of the polynomials are inserted into the first row. So remember, 2x cubed minus 13x squared minus 10x plus 21 was the third order polynomial we started off with. In the bottom left corner, we will insert the 0 of the polynomial. So recall that p of x was equal to 0 when x was equal to 1. So 1 is in fact the 0 of the polynomial, or one of its zeros. So first step is we will just rewrite the first coefficient in the bottom row. So in this case we're just rewriting 2, which was the coefficient for x cubed. Now we're going to multiply 1 times 2 and insert the result under the second column of the coefficients. In this case, 1 times 2 is 2. And then we will add the elements of the same column. So minus 13 plus 2 is minus 11. And then we'll do it again. 1 multiplies with minus 11 to result in minus 11, which we write under the next coefficient. And then we proceed by adding the coefficients that appear there. Minus 10 plus minus 11 is minus 21. And we go on until we get to the last column. So same again. 1 multiplies with minus 21. Minus 21 is the result of this multiplication. And finally, when we add 21 with minus 21, we will get 0. All right, so how does this provide the answer to our division? Well, 2 minus 11 and minus 21 are actually the coefficients of the quotient. And remember, I said it would be a second order polynomial since we had divided a third degree polynomial by a first degree polynomial. 0 is the remainder of the long division, and if you do not get 0, it means something went wrong either in the synthetic division or in your computation of what you thought was a 0. Okay, so in conclusion, 2x squared minus 11x minus 21 is actually the quotient obtained from our long division, or in this case, our synthetic division. Okay, so 2x cubed minus 13x squared minus 10x plus 21 divided by x minus 1 is 2x squared minus 11x minus 21. So basically, our third degree polynomial is now factored or split up into the product of x minus 1 with the quadratic 2x squared minus 11x minus 21. Now we're in more familiar territory because in the case of quadratics, we can use procedures we've learned in the past. Notably, in this case, we could use the sum product method, looking for two numbers, m and n, that recreate the same number as the product of a with c minus 42, and two numbers whose sum replicates the value of b, which is minus 11. We'll find minus 14 and 3 to respect both of these conditions. Okay. So now we've used minus 14 and 3 to split up what used to be the bx term, or the minus 11x term, and we've created two pairs of terms that we can factor by grouping. From the first pair, 2x is common, which leaves x minus 7 as its multiplier. From the second pair, 3 is common, which leaves x minus 7 as well as its multiplier. And since x minus 7 is now a common factor, it can be extracted. And now we have our factored form for this higher order polynomial. As you can tell, using the factor theorem can be of great help, especially when a zero of the polynomial is either known or given. Now, you may want to speak to your teacher about what to do when the zero is not known or not given. So this will come from a trick that is called the rational roots theorem. Having to use the factor theorem and then the synthetic division can be quite tedious though. So remember to investigate more direct methods beforehand. That is, can you do simple factoring first? Can you do grouping first? Perhaps have you recognized that there is a special factoring form to be used? Otherwise, you're stuck doing the long